Hello everyone. In the next few videos, we will go through some of the preliminary material required for the course. In this video, we'll look at some concepts related to inner products and norms. I will cover this material very quickly because it is assumed that you already know it. However, if you get confused at any point, please pause the video and work it out. If you still do not get it, a quick Google search might help. Of course, you are free to post your questions on the course forum if you are still confused. Let us begin with detailing some notation. We will generally be dealing with elements such as x that belong to a vector space V over a field F of real numbers R. Example of a vector space is Rn, which is the space of all column vectors of size n cross 1. Another example is Rm cross n, which is the space of all matrices of size m cross n. Such a vector will be denoted by small letter with underline. The notation here says that X is in Rn. Usually in books and papers we use bold font X, but that is difficult to do in handwritten notes, so we have to use the underline. Sometimes I might forget to put the underline, but it should be clear from the context if I am talking about a vector or a scalar. Such matrices will be denoted by capital letter X. Note that we are purposefully trying to be rigorous and general so as to include all possible cases. Most algorithms can actually be applied to vectors and matrices. But if you are not very comfortable with the general notation and rigor, in the first pass through the course material, try to imagine X as a vector. That could even simplify some of the proofs and help you understand. You can try to appreciate the generality of the results when going through the material the second time. Let us recap the eigenvalue decomposition. Consider a square symmetric matrix Q in R n cross n. Such a matrix can be written as U times capital lambda times U transpose, where U is an n cross n orthogonal matrix. Recall that for an orthogonal matrix, it is the one that satisfies U times U transpose equal to U transpose times U equals identity. In other words, U and U transpose are inverses of each other. The n cross n matrix capital lambda is diagonal and its diagonal entries are given by lambda 1 to lambda n. Here the diag with capital D is a function that takes few inputs and arranges them along the diagonal of a square matrix. These lambda I of Q are called the eigenvalues of Q, and the columns of U are called the eigenvectors of Q. Note that you might have seen a more general definition of Q equal to U lambda U inverse, which is applicable for general square matrices. For symmetric matrices, we can use the specialized definition where U inverse is U transpose. We will mostly be dealing with symmetric matrices, so we need not worry about the general case. Also, symmetric matrices have a very nice property that their eigenvalues are all real. Please try to prove this property. This brings us to the notion of positive semi-definite matrices. As we have already seen in the earlier video, a symmetric matrix Q is said to be positive semi-definite if either of the following hold. The eigenvalues of Q are all non-negative. Equivalently, U transpose QU is non-negative for all U in Rn. Here the entries of U can be positive or negative, it doesn't matter. The quantity U transpose QU will always evaluate to something non-negative. If you choose U such that only one of its entries is 1 and all others are 0, then U transpose QU will evaluate to a diagonal entry of Q. Therefore, the second condition implies that for any PSD matrix Q, all its diagonal entries must be non-negative. Finally, the third equivalent condition is that Q can be factorized as a product of the form L times L transpose, where L is any n cross m matrix for m less than or equal to n. In fact, m can be anything, but the smallest value of m is the rank of Q. If you have not seen this property before, you can pause the video and try to show that the third property follows directly from the second property. We remarked that in the same way, one could say that Q is positive definite if its eigenvalues are strictly positive. A positive definite matrix is full rank and invertible. Please take a moment to derive the other two properties for positive definite matrices. A related concept is that of singular value decomposition, which can be applied to arbitrary m cross n matrix. If X is an R m cross n, its singular value decomposition is given by U times capital sigma times V transpose. Here, U is an orthogonal M cross M matrix, capital sigma is an M cross N matrix, and V is an orthogonal N cross N matrix. While capital sigma is rectangular matrix, only the entries along its main diagonal are non-zero, and its I comma ith entry is written as sigma I of x, which is the ith singular value of x. The columns of U and V are its left and right singular vectors respectively. I must point out that by definition, singular values are always non-negative. The rank of the matrix X is the number of non-zero singular values of X. There are other ways of writing down the SVD. Note that many of the entries of sigma might be 0, so many of the columns of U and V are being multiplied by 0. A more compact version of SVD is when you remove the 0 rows and columns of sigma and corresponding columns of U and V. In that case, sigma becomes R cross R, where R is the rank of X and U and V become rectangular. The compact decomposition is useful when dealing with large matrices because you do not want to waste time calculating all those singular vectors that you are going to multiply to 0. The singular value decomposition and the eigenvalue decomposition are closely related. In fact, consider a matrix X transpose X, which is the square and symmetric matrix of size M cross M. If we substitute the singular value decomposition of X here, we obtain V capital sigma transpose U transpose U capital sigma V transpose. Recall that U is orthogonal, so U transpose U is identity. Therefore, the expression becomes V sigma V transpose. Here, since sigma is M cross N matrix with singular value along its main diagonal, sigma transpose sigma would be an M cross M diagonal matrix. Together with the fact that V is orthogonal, this is exactly the eigenvalue decomposition of X transpose X, with V containing the eigenvectors and sigma transpose sigma containing the eigenvalues. In fact, if you multiply these two matrices carefully, you will see that the ith diagonal entry, which is essentially the ith eigenvalue of X transpose X, is exactly the square of the ith singular value. Clearly, if the rank of X is R, then there are R non-zero singular values of X and correspondingly R non-zero eigenvalues of X transpose X. Observe that if a matrix is square, symmetric, PSD, then its eigenvalue decomposition and singular value decomposition are exactly the same. Therefore, for PSD matrices, the eigenvalues and singular values coincide. For all other cases, the two would generally be different because singular values are always constructed to be non-negative. Now let us look at inner products and norms. Inner product between two elements X and Y is written like this. Its definition is, however, dependent on the vector space being considered. For instance, when considering Rn, the inner product is given by X transpose Y. Likewise, when considering Rm cross N, the inner product is given by trace of X transpose Y. In both these cases, you can also get the inner product by taking element-wise product of X and Y and adding up all the entries. I hope you have seen this many times, so I need not explain these in more detail. A norm is a function from V to R plus, which is the non-negative real line. This notation is another way of saying that the norm function takes as input an element of V and outputs a non-negative number. The norm function satisfies three properties. First is that the norm of alpha times X is equal to the absolute value of alpha times the norm of X, where alpha is a scalar. The property is called the homogeneity property or scaling property. The second property is that norm of X plus Y is less than or equal to the norm of X plus the norm of Y. This property is called the triangle inequality. The third property is the norm of X equal to 0 if and only if X is equal to 0. In other words, norm of the 0 element is 0, and if the norm of an element is 0, then that element has to be the 0 element in V. This property is called the definiteness property. Together, these are the three key properties of the norm function, and in fact, any function satisfying three properties is a valid norm. There is also a class of functions which only satisfy the first two properties, but not the third property. And these are called semi-norms. So let us take a look at some examples of norms and semi-norms. For vectors, we have the LP norm, which is defined for all p greater than or equal to 1. The LP norm is the pth root of the sum of all the entries raised to the pth power. We also define the LP norm for p equal to infinity as the entry of x with the largest absolute value. You may recall that for p equal to 2, this is known as the Euclidean norm. The Q norm is defined for any positive definite matrix Q. Let me just emphasize that this notation Q greater than 0 means eigenvalues of Q are greater than 0. This is a special notation that we are using in the matrix context, and it is not applicable entry-wise. In fact, a number of operators can be applied to matrices. Examples include less than, greater than, square root, power, exponential, logarithm. Each of these operators in the matrix context means that they are being applied to the eigenvalues of the matrix and not the individual entries. The Q norm for a positive definite matrix Q is defined as the square root of x transpose Qx. Recall from the properties of the positive definite matrices that the quantity x transpose Qx is always positive unless x is 0 and actually satisfies all the properties of the norm. As an example, suppose that Q is a diagonal matrix with entries Q1, Q2 till Qn, all positive. In that case, Q norm is given by square root of sum over I Qi xi square. The Q norm can be seen as a kind of a weighted norm where Q is the weight matrix. If you imagine the norm to be a length of a vector, then to calculate Q norm, we are basically rotating, reflecting, squeezing and stretching the vector in various directions before calculating its length. These transformations depend on Q and more specifically on the eigenvalues and eigenvectors of Q. So what happens if Q is positive semi-definite instead of being positive definite? In other words, some of its eigenvalues could be 0. To get some intuition, consider what would happen if one of the Qi's in this example here were to be 0. You can see that the norm would then evaluate to 0 even if that corresponding entry of x was non-zero. In other words, making one of the Qi's to be 0 would result in this function not satisfying the definiteness property. Interestingly, the homogeneity and triangle inequality properties are still satisfied, so this function then becomes a semi-norm instead of norm. The symmetric square root of a positive semi-definite matrix is defined as the symmetric positive semi-definite matrix P such that Q is equal to P times P. In general, the symmetric square root decomposition exists for any PSD matrix Q. So if we were to substitute Q in the expression for the Q norm, we would see that it would equivalently be written as L2 norm squared of the vector P times X. So here we can see that if Q was positive semi-definite, then the norm of P times X would be 0 for all X in the null space of P. The null space of P is non-empty whenever the rank of Q is less than n, or equivalently one or more of its eigenvalues are 0. So how to find P? We can carry out the eigenvalue decomposition of Q and write the diagonal matrix capital lambda as square root lambda times square root lambda. Then introducing U transpose U in between, we can see that P is equal to U times square root lambda times U transpose. Note that for a diagonal matrix with non-negative entries, its square root is simply the square root of its diagonal entries. In other words, applying the square root operation on Q amounts to taking square root of its eigenvalues, while keeping the eigenvectors same. Next, let us take a look at some examples of matrix norms. The LPQ norm for M cross N matrix X is defined as follows. If you observe closely, you can see that this norm entails taking the LP norm of each column of X, forming an n cross 1 vector out of the resulting values, and then taking the LQ norm of the resulting vector. A particular example is the Frobenius norm, which is basically the L2 norm of the vectorized version of X and occurs for P equal to Q equal to 2. Here vec of X denotes the Mn cross 1 vector formed by stacking the entries of X. Another way of writing the Frobenius norm of X is the square root of the trace of X transpose X. If you remember, the inner product of X in R M cross N was defined as trace of X transpose Y. The Frobenius norm is thus derived from the inner product. Alternatively, the Frobenius norm is simply the square root of the sum of squares of all the entries of X. Finally, the Frobenius norm is also the square root of the sum of squares of the singular values of X. You can establish this last result by carrying out the singular value decomposition of X and then using the trace definition. Please convince yourself that this is indeed the case. The Frobenius norm and more generally the LPQ norms are entry-wise norms in the sense that they are expressible as a closed form expression of the entries of the matrix X. This was also the case with vector norms. However, there are a number of other matrix norms that are not entry-wise. Further, these norms will be very useful, so we cannot avoid them. Let us look at some examples of other matrix norms that are usually not expressible as a closed form expression of their entries. In case you are seeing these norms for the first time, do not worry too much at this stage. We will actually go through the properties of some of them later in the course. Another commonly used matrix norm is the operator norm, again denoted by X subscript PQ. The operator norm is given by the maximum over all non-zero U of LQ norm of X times U divided by LP norm of U. An equivalent definition is the maximum over all U with unit LP norm of the LQ norm of X times U. The operator norm is also called the induced norm. If you have not seen this norm before, you would have observed the complicated definition as it involves a maximization operation. While working with the proofs, we would not really need to solve it explicitly, just use the properties of LP and LQ norms and the maximization operation. For instance, one property that follows directly from the definition of the operator norm is that the LQ norm of XU is less than or equal to the PQ norm of X times LP norm of U. You can infer this property from the first definition above. Basically, there must be some non-zero U for which the maximum in this definition is attained. So for that U, we have the equality here. So that means that PQ norm of X is greater than or equal to the objective function written here for an arbitrary U. That is exactly what the inequality is saying. The operator norms are actually general and can be defined for arbitrary operators in the vector space. When I say an operator, I mean a functional which takes input an element in V and outputs an element in V. So a matrix can be treated as a linear functional that takes input U, which is an element in V, and outputs XU, which is a linear transformation of U and is also in V. The operator norms are not something exotic but are actually widely used in a number of fields. So it helps knowing them. A special case of the operator norm is the spectral norm, which is for P equal to Q equal to 2 and is given by the maximum singular value of X. Another example is the Schatten norm of X, which is essentially the pth norm of the singular values of X. A special case of the Schatten norm is the very popular nuclear norm, which occurs for P equal to 1 and is given by the sum of singular values of X. The nuclear norm is considered to be the matrix counterpart of the L1 norm. So like L1 norm is used in regularization, the nuclear norm is also used as a regularization function in optimization problems where the optimization variable is a matrix. The nuclear norm can be seen as proxy or an approximation to the rank of the matrix. But the rank of the matrix is a non-convex function of that matrix. So when the goal is to minimize the rank, one may resort to minimizing the nuclear norm, provided that the resulting error due to this approximation is acceptable. The idea of using nuclear norm as a proxy for the rank was, for instance, used to solve the Netflix price problem that we discussed in the first video. With this, we conclude our discussion on the basics of inner products and norms. Before concluding, however, let me make an important remark. As we mentioned, we will generally operate inside a vector space. In fact, we will only be concerned with a normed vector space, that is one where a norm can be defined. Henceforth, whenever we mention the word vector space, you can assume that we are talking about a vector space and a norm. An important subset of the normed vector spaces are the inner product spaces. An inner product space is one for which the norm is derived from the inner product. That is, the norm of x is the square root of the inner product of x with itself. For instance, in Rn, the norm of x with itself defines the Euclidean norm. Likewise, in Rm cross n, the inner product of x with itself yields the Frobenius norm. Another example of an inner product space is the reproducing kernel Hilbert space, which is widely used in machine learning. Note that not all normed spaces are inner product spaces. For instance, there does not exist any inner product definition that leads to the L1 norm. Therefore, a normed vector space associated with the L1 norm is not an inner product space. So many of the results developed in this course would be general and they would apply for the normed vector spaces, but some will be specialized to inner product spaces. So that is all for this video. We'll continue in the next video.